In this episode, we're going to focus on the most important idea in OT security. Safety comes first, and the purpose of protecting operational systems is ultimately to protect people, the environment, and reliable service. For beginners, it can be tempting to think of cybersecurity as a contest of hackers versus defenders, or as a problem of protecting computers from malicious software. In industrial environments, computers and networks are tied to physical processes, and those processes can create real-world harm if they are mismanaged, disrupted, or manipulated. That means OT security has a different North Star than many office environments. The goal is not only to prevent data loss or reduce inconvenience, but to prevent outcomes like injury, loss of life, environmental release, and uncontrolled process behavior. Reliability also matters because predictable, stable operations reduce the chance of dangerous conditions and reduce the likelihood that people will take risky shortcuts under pressure. As we go, we'll talk about what safety outcomes mean, why they change how we prioritize risks, and how to think about trade-offs without becoming overly technical or tool-focused. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful place to begin is to understand why safety is not just another impact category in OT, but a primary constraint on all decisions. In many business contexts, you can trade time for money or accept inconvenience to reduce risk, and those trade-offs are common. In safety-critical contexts, there are boundaries you do not cross because certain outcomes are unacceptable regardless of cost. If a decision could plausibly contribute to loss of life or serious harm, it requires a much higher standard of care. This is why OT security often emphasizes availability and integrity, because unsafe outcomes can occur when systems are unavailable at the wrong time or when data and control logic are incorrect. A system that is secure but causes operators to lose visibility during an abnormal process condition is not truly safe. Similarly, a system that is available but can be manipulated to show false readings is dangerous because it can lead to incorrect actions. Beginners should learn that in OT, safety is not a side concern. It is the lens through which security is judged. Loss of life is the most severe safety outcome, and it can occur through direct and indirect pathways. Direct pathways involve control systems affecting equipment that can harm people, such as high-pressure systems, rotating machinery, high-voltage equipment, or processes involving hazardous materials. If control signals are disrupted or manipulated, equipment might behave unpredictably, safety limits might be exceeded, or emergency responses might not trigger correctly. Indirect pathways involve human factors, such as operators making decisions based on wrong information or being forced into manual operations under stress. For example, if monitoring systems are unavailable or untrustworthy, operators may have to rely on limited local indicators and may miss early warning signs. In a crisis, teams might improvise, and improvisation increases risk. The cybersecurity connection is that attackers do not need to aim for harm to create conditions where harm becomes more likely. A disruption that delays alarms or confuses readings can increase danger even if the attacker's original goal was only disruption or extortion. Beginners should understand that safety outcomes are often about conditions and sequences, not a single dramatic action. Environmental harm is another major safety outcome, and it is especially relevant in industries that handle chemicals, fuels, wastewater, or processes that produce emissions. Environmental harm can occur if containment systems fail, if monitoring systems do not detect leaks, or if control systems mishandle pressure, temperature, or flow in ways that lead to release. Environmental impacts can range from localized damage to large-scale events that affect communities, waterways, and ecosystems. Like loss of life, environmental harm can be caused by loss of availability or loss of integrity. If a monitoring system goes down during a critical period, a leak might not be detected quickly. If sensor data is altered or delayed, decision-makers might believe conditions are normal when they are not. Recovery from environmental incidents is often complex and long-lasting, involving cleanup, regulatory reporting, community trust, and financial penalties. That means environmental harm is not only an ethical and safety issue, but also a major business continuity issue. Beginners should see that protecting the environment is part of OT security's purpose, not an optional extra, because the systems being protected often exist to keep processes within safe limits. Reliability expectations might sound less dramatic than life and environment, but reliability is deeply connected to safety. Reliability in OT means that systems behave predictably and consistently, that control loops remain stable, and that operators can trust that the process will not surprise them. Unreliable systems force humans to compensate, and human compensation often involves shortcuts, workarounds, and fatigue, which can create unsafe conditions. For example, if alarms are frequently noisy or inaccurate, people learn to ignore them, and then a real alarm can be missed. If systems frequently reboot or lose connectivity, operators may lose confidence in automation and may switch to manual operation, which can be riskier depending on the process. Cybersecurity incidents can directly reduce reliability by causing outages, degrading performance, or introducing subtle errors. Even security controls themselves can reduce reliability if they are applied without operational understanding, such as a change that blocks necessary communication or causes unexpected latency. Beginners should learn that reliability is not only a performance metric, it is a safety factor, and OT security must preserve it while reducing risk. When we talk about prioritizing safety outcomes, we are really talking about how to rank risks and choose controls when resources and time are limited. In OT, risk prioritization often begins with understanding which systems, processes, and scenarios could lead to unacceptable safety consequences. That means identifying where a cyber event could influence safety-critical functions, such as emergency shutdown behavior, safety instrumentation, process interlocks, and operator visibility during abnormal conditions. It also means recognizing that not all systems are equally tied to safety. A reporting dashboard might be useful but not safety-critical, while a system that provides key process measurements might be essential for safe operation. Prioritization also considers how quickly harm could occur and whether there are independent protections. Some processes have multiple layers of protection, such as mechanical relief valves and independent safety systems, while others rely more heavily on automation and monitoring. The goal is not to memorize specific safety standards, but to build the habit of asking, if this system fails or lies, what could happen in the real world? A key concept for beginners is that safety is often protected by layers, and cybersecurity is one of those layers rather than the only layer. Industrial safety commonly relies on designs that assume failures will happen and that provide safeguards to prevent those failures from becoming disasters. Cybersecurity adds value by reducing the chance that failures are triggered intentionally and by reducing the chance that the safeguards themselves are bypassed or degraded. But cybersecurity also must respect the existing safety layers and not interfere with them. For example, segmentation and access control can reduce the chance of unauthorized changes to safety-related systems, while monitoring can help detect abnormal communication patterns that might indicate tampering. At the same time, overly aggressive security actions like automatic blocking of traffic could interfere with safety communications if not designed carefully. That is why OT security emphasizes careful change control, testing, and collaboration with safety and engineering teams. Beginners should understand that prioritizing safety outcomes includes prioritizing safe security practices, meaning security that does not create new hazards. Another important idea is the difference between stopping harm and proving safety. In safety-critical contexts, it is not enough to hope that a control helps. You need confidence that the control will behave correctly under real conditions. That is why evidence, testing, and disciplined procedures matter so much in OT. If a segmentation rule is meant to isolate a safety system, teams need to verify that it does not break required communications and that it actually blocks the unwanted pathways. If remote access is allowed for vendor support, teams need to ensure that access is controlled, logged, and time-limited so that it does not become an unmonitored doorway into critical zones. If monitoring systems are used to detect tampering, teams need to ensure that those systems remain available during incidents and do not depend on fragile external connectivity. For beginners, this can be summarized as safety-driven security requires trustworthiness, and trustworthiness comes from design and validation, not from good intentions. The more severe the potential outcome, the higher the bar for trustworthiness. Human factors also matter in safety prioritization because people are part of the control system in many OT environments. Operators, technicians, and engineers make decisions based on the information they receive and the procedures they are trained to follow. Cyber events that confuse, overwhelm, or mislead people can increase the chance of unsafe actions, even if no equipment is directly manipulated. For example, if an attacker generates a flood of false alerts, people may struggle to identify what is real, and a real abnormal condition could be missed. If displays show inaccurate readings, people may make adjustments that worsen the process. If systems are unreliable, people may develop workarounds that bypass safeguards. Security programs that prioritize safety outcomes should therefore include attention to clarity, usability, and training, even if this episode is not about training programs specifically. The beginner takeaway is that safe systems support clear decision-making, and cybersecurity should protect the integrity of the information humans rely on. Environmental and reliability expectations also shape recovery decisions after incidents, because returning to service must be safe, not just fast. In a typical office environment, you might rebuild a system and get users back online quickly, accepting some uncertainty as you investigate later. In OT, uncertainty can be dangerous because if you restore operations without confidence in control integrity, you might reintroduce unsafe conditions. Recovery may require verifying control logic, checking configurations, validating sensor calibration, and ensuring that monitoring and safety layers are functioning properly. It may also require coordination with safety and engineering to determine safe operating modes during the recovery period. This can feel slow compared to IT recovery, but it is appropriate because the consequences are higher. Beginners should learn that recovery time is not the only goal. Safe recovery is the goal, and sometimes that means a deliberate, staged return to normal operations. As we wrap up, prioritizing safety outcomes in OT security means treating loss of life and environmental harm as unacceptable outcomes that shape every decision, and treating reliability as a core safety factor rather than a nice-to-have. It means recognizing that availability and integrity failures can create unsafe conditions, and that cyber incidents can influence safety both directly through control systems and indirectly through human decision-making. It also means understanding that safety is protected by layers, and cybersecurity is one layer that must strengthen the whole system without interfering with other safeguards. When you can explain why certain systems deserve stronger protections because they are tied to safety-critical functions, and why controls must be validated and governed carefully because mistakes can create hazards, you are thinking the way OT security expects. The goal is not to make operations harder. It is to keep people safe, protect the environment, and maintain reliable service in a world where both accidents and attackers can create dangerous disruptions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.